So normally when I give the live class, I don't have anything planned for the final lecture. So welcome to the final lecture of Machine Learning from Data, lecture 28. And I open up to the class and you can ask me whatever you want. But in this online version, that's a little tough to do. And anyway, when I allow the class to ask me whatever they want, they typically want to know about one of two things, either aggregation or reinforcement learning. Reinforcement learning is a little bit more popular. So I thought, since I have nothing planned, let me just talk about aggregation and reinforcement learning. If you want to listen, listen. If you don't want to listen, go and work on the homework. Okay. So let's start with aggregation. Aggregation. Okay, so what is it? At a high level, it just means combining models. So at a high level, it just means combining models. Okay, and there are sort of two modes in which you can think about combining models, i.e. aggregation. One mode is sort of during learning, sort of we can call that before the fact, and we could consider that as some form of ensembling during the learning process. Okay, so there are two modes. Before the fact, i.e. during learning, okay, so as you are performing the learning, you have the hypotheses that are generated H1 of X, H2 of X, and so on, HT of X. As you learn, you try out, you gradually produce, and typically simple hypotheses. So simple hypotheses. And then during the learning phase, you combine these hypotheses. Okay, and you produce your final hypothesis, G of X, is combined. Okay, and a very famous example of this is what's called boosting, and it has led to sort of techniques like random forests. So, for example, boosting, random forests is a good example of boosting. Okay, now you can read more about boosting. So aggregating little simple hypotheses, during the course of learning in order to form a more complex hypothesis, and it typically works pretty well. So combining models during the learning phase, aka sort of something like boosting. Okay, before the fact aggregation, and then there's after the fact aggregation. So after the fact aggregation, i.e. after learning. And I call this the supervisor's problem. So this is the supervisor's problem. Okay? And sometimes it's called blending. Blending. And a version of this is sometimes called bagging. Bagging. Okay, so what's the problem that is going on here? Okay, so what's the idea? What's the scenario? Okay, so and why do I call it the supervisor's problem? You think there's a supervisor, and the supervisor has given a machine learning problem to 5 peons or 10 peons or m peons, and they each produce a hypothesis G1, G2, G3, G4 up to Gm. Okay, now in general, the supervisor doesn't know what these people have done. Okay, so there are some choices that the supervisor can sort of do in order to decide what's the final hypothesis. So they gave their finalists, and now I'm the supervisor. I need to decide what's the final hypothesis. So I start with hypotheses G1, G2, G3, let's say up to Gm. And I have to produce a final hypothesis G of X. So these are all of X. Okay. Now, one thing the supervisor could have done is kept aside a test set, and we'll discuss what to do there, when we come to talk about blending. Okay, but if the supervisor doesn't really trust any of their out of sample estimates, any of their e-ins or e-outs or e-validation or whatever, because I don't know what has gone on in here, then one thing the supervisor can do is just pick one of these at random. So G of X is one of the GI at random. So what's the out of sample error? The out of sample error is equal to, the expected value of GI of X minus y, whatever y happens to be. Let's say we're doing the squared error. Okay, or some error that's basically a convex error, but let's just work with the squared error to be simple. So this is my out of sample error if I pick hypothesis I. Okay, and since I pick randomly, I expect on average my out of sample error will be the average of these out of sample errors for each of the individual finalists that were produced by my subordinates. Okay, so my average out of sample error, average, my expected, what is the out of sample error I'm expecting, is 1 over m, the sum from I equals 1 to big M of the average of the errors made by each individual hypothesis. Okay, so that's certainly one option. Another option, which is called the bagging option, is don't pick one of these at random, vote them, take the average. Makes sense, right? So g of x is equal to 1 over m, the sum from I equals 1 to big M of gi of x. Okay, it's interesting. We can analyze the out of sample error of this bagged version. So let's do a quick computation. I don't like to do detailed computations on the last lecture, but okay, let's do a few. You can always fall asleep if you want. Okay, so what's the expected out of sample error of this guy? So E out for this guy is equal to, so let's call this a random choice. This is random choice. And this E out of G, so bagged, so G of x, so this is bagging. Okay, E out of G is equal to the expected value of G of x minus y squared. And now this G has combined all of these guys. So this is the expected value of 1 over m, the sum over I, gi of x minus y squared. Okay, I just replaced G by the sum over m, gi of x. Okay. And now what I can do is, this is a sum of m terms. I can split up this y into m terms, each of size y over m. And so I can rewrite this as the expected value of the 1 over m, okay, the sum from I equals 1 to m of gi of x minus y, and that quantity squared. Okay. So you can think of this as the error made between gi and y averaged, and then I square it. Okay. So if I wanted, I could write this as okay. Let's you can call this epsilon I of x, the error made by function I. So this is the expected value of the average error 1 over m, sum from I equals 1 to m epsilon I of x, the error made by function I take the average of those and then I square. Okay. Now, one of the properties of the expected value is that this guy is equal to, I can take the expected value outside the sum, okay, because the expected value and sum commute, and expected value and multiplication commutes. So this is equal to the expected value of 1 over m, okay, times the sum from I equals 1 to m. And this is the error made by hypothesis gi. It's that error squared. Okay, epsilon I of x squared. Okay. And we see a very interesting similarity here. Okay. This is the average of squares. This is the average of those same things. It's the average squared. The average of squares is always larger than the average squared. So this guy is always larger than the expected value of the sum from I equals 1 to m of epsilon I of x 1 over m, that quantity squared. Because look, this guy here is the average of squares. This is the average squared. And that's a fundamental property. Okay? This is true for any function that is essentially satisfying some kind of a convexity property. Okay, but what have we proved? We have proved that the out-of-sample error that you incur when you pick one of these hypotheses at random is always larger than the out-of-sample error you incur when you average the hypothesis. So when you vote these and average, okay, so when you vote them in the form of an average, the average hypothesis, the average of the hypothesis is always better than picking a random. Okay? So conclusion. The average is always better than picking one at random. Interesting. Okay. It's an interesting little conclusion that comes out of this analysis. And so that might lead us to suspect that, hey, maybe we can do a more sophisticated kind of averaging. Okay. So maybe instead of taking the uniform average, maybe g of x should equal, the sum from I equals 1 to m of alpha I times, gi of x. So more sophisticated, weighted average. So this is now a weighted average. Okay, and indeed you can figure out what are the optimal weights. So if your supervisor had kept a test set aside, so then let's see, what's the error made? So g of x minus y, okay, is equal to, so let's imagine that gi of x is equal to y plus epsilon I of x. So the error made. So each hypothesis I makes some error. So then g of x minus y, the error made by the hypothesis g of x is equal to the sum from I equals 1 to big M alpha I of gi of x, which is y, plus alpha I epsilon I of x. Okay. And then you subtract the y. Okay, so if we assume that this weighted average has a sum of alphas equal to 1, then this is the sum of alphas times y minus y. Okay, and so the error made by this weighted average is just the weighted average of the errors made by each individual hypothesis. So this is just the sum from I equals 1 to big M alpha I epsilon I of x. Okay. So if I want to minimize the squared error, so I want to minimize the expected value of g of x minus y squared, then I want to minimize this guy. I want to minimize this thing squared, which is the sum from I equals 1 to m alpha I epsilon I of x, the sum from j equals 1 to m alpha j epsilon j of x, okay, which is in terms of in expected value, okay, which is equal to the sum from over I and j alpha j epsilon j. So it's the expected value of the sum over I and j alpha j epsilon I of x epsilon j of x. Okay, and then that's equal to, I can take the expected value inside the sum, so that's equal to the sum over I and j alpha j, the expected value of epsilon I of x epsilon j of x. Okay, so what it turns out is that I don't need to know the actual behavior of the errors. I only need to know the expected value of the products between two different errors. So these are basically what we call the correlations between the individual hypotheses, which I've now erased them. So you have G1 up to Gm. These are the correlations between the errors of the individual hypotheses. Okay. So we can call this matrix of correlations Cij. So then this term here is just alpha transpose C alpha. So if I can somehow estimate the correlations between the errors of these different hypotheses, okay, then I can compute the error made by a weighted average, and then I can optimize this guy under whatever constraints I want. So the simplest constraint is that this is a weighted average, so 1 transpose alpha equals 1. You could also require that every hypothesis must have a non-negative weight. You're not allowed to have negative weight, so alpha greater equal to 0. And if you know C, then this is a quadratic program. Okay. Now, how might the supervisor estimate C? Well, all the supervisor needs to do is have left aside a small test set, and the purpose of the test set is not to sort of see what is E out, it's just to estimate the correlations between the hypotheses. Estimate this correlation matrix between the errors made by my various hypotheses that I got. Okay, if I can estimate this C, then I solve this quadratic program. Boom! I've got the optimal weights, and I've got the optimal, in some sense, the optimal weighted combination of my subordinates, learned final hypotheses. Okay. If you don't have this constraint, if you don't have the alpha greater equal to 0 constraint, then we can actually solve this problem exactly. With Lagrange multipliers, it's easy to show that alpha star is equal to C inverse 1 over 1 transpose C inverse 1. Okay? So there. So, there are principled ways of aggregating. Okay? What that means is combining hypotheses, ensembling them. And now if you want to read more, you can read up about ensemble methods, you can read up about boosting, you can read up about blending, bagging, and so on and so forth, but this is the general idea. Before the fact, during learning, we might, produce simple hypotheses and figure out a good way to combine them to produce our final hypothesis. And after the fact, after learning, so a whole bunch of people have already learned and produced final hypotheses. You're the supervisor. You need to figure out what to do with them. You don't want to pick a random one. It's always better to just take the flat average. Or you can blend them together. And all you need to know is an estimate of the covariance matrices. Okay, let me erase and come back and talk about reinforcement learning, which is usually a big ticket item. Everyone wants to know about reinforcement learning because it seems so natural. It's the way humans predominantly learn. Before we hit reinforcement learning, I just want to give you a little exercise. It's a fun exercise. You can do it. Okay, it'll give you an appreciation for when, why, and how aggregation works. And the basic idea is you might have many sort of weak, not so good hypotheses, and you're going to combine them in some way, in order to get a strong hypothesis. And when does that work? So, it's really the tale of the Smurfs and Einstein. Okay, so you have Smurfs, and let me try to draw Smurfs. They've got these fancy hats. Okay, and that's what a Smurf looks like. Okay, and then you've got Einstein. That's Einstein. Okay, and so this is Einstein. Okay, and you've got your Smurfs. Okay, and what do I aim to capture with this sort of notion of Smurfs is that there are many Smurfs. Okay, but they're really random little weak creatures. So random, weak, decision makers. So they roam around and, say yes or no randomly. Okay, so they're random and weak. Let's say that, they have an accuracy of 55%. If you ask them a question, they'll answer correctly 55% of the time, and it's kind of random. So they're almost a coin toss, but slightly better than random. Okay, so 55% correct. Okay, and you have Einstein, a strong guy. He was even asked to be the president of Israel. Okay, so Einstein, he is correct. 99.9% of the time correct. Okay. And, who you want to be the president of your country, Einstein, or 1,000 Murphs, 1,000 little noisy, annoying, random creatures roaming around saying yes or no randomly to answers. So 1,000 Smurfs versus 1 Einstein. Okay, who would you pick? Okay, and it really depends on the nature of the Smurfs. If all the 1,000 Smurfs have just one leader and, all of them say whatever that one leader says, then basically, the correct decision will come whenever the one leader makes the correct decision. Or Smurfs are really disorganized, completely random little annoying creatures that run around screeching, okay, and they are all independent. So let's consider the case where all the Smurfs are independent. Smurfs are independent. Okay, and when I showed you some of the sort of math related to aggregation, you saw that what came into play was the correlations between the errors made by your individual, weak hypotheses. So the Smurfs are independent, okay? And, we could ask, okay, what do I do with 1,000 annoying, random, independent Smurfs running around? I can ask them all the same question, and then whatever the answers are, take the majority vote. So I can take the majority vote. Okay. So now, would you rather live in the world where you have 1,000 annoying Smurfs roaming around randomly answering questions 55% of the time correct for each Smurf, or Einstein, who gets the question right 99.9% of the time. And so this is a very interesting exercise for you to do. So if you had n Smurfs, the probability that you get the correct answer from the n Smurfs, now this is an exercise for you, is basically the sum from I equals, let's assume n is even, so the sum from I equals n over 2 plus 1 to n of n choose I, p to the I, 1 minus p to the n minus I. Essentially, this is the probability that a majority of the Smurfs make the correct answer. And p here is 0.55. So it's an exercise for you to show that this is the probability that the majority vote among n Smurfs is correct. And you can certainly compute this number, for n equals, let's say, 100, 500, 1,000. So n is, so go ahead and do this exercise. And it's a very interesting exercise to do, not just from the perspective of Smurfs and Einstein, but how are you going to compute this guy? This is a very numerically unstable computation. Because what ends up happening is you're taking big numbers, multiplying them by small numbers, multiplying by another even smaller number. So if you compute this big number, multiply by 0, which is what's going to happen when I gets large, multiply by 0 when n minus I is large. So basically you get 0 to numerical precision if you just do this in a naive way. So there's some computer science skill involved in computing this number. But let's say you compute this number, the probability that n Smurfs give you the correct answer when you take a majority vote. And you will find, let's say for n equals 100, let's do 500, and let's do 1,000. And it shouldn't come as a surprise to you that I picked the 1,000 Smurfs to illustrate the point. So at 100, the probability that your Smurfs are correct is approximately 81, 82%. 82%. I'm not sure the exact number. And with 500 Smurfs, the probability all of a sudden jumps with 500 little random creatures running around. 98.6%. And then at 1,000 Smurfs, it's approximately 99.92%, 0.02% more accurate than Einstein. Now, let me tell you what was key here. There are two keys. Three keys. The first is that your Smurfs they might be weak, but they're better than random. Slightly better than random. 55% correct. And you have many of them. In this case, 1,000 was enough. But the real key is the independence. So they're all giving you independent opinions. And when you get independent opinions, majority vote, beats one strong vote. And this is really in some sense, the basis for kind of democracy. And why 250 or 300 million voters, even if they're all just slightly above random, why they will come up with the right decision. You might wonder, what happens if they're not all slightly above random? So this is really a two-edged sword. What happens if this becomes 49% or let's say 45%? What happens if your voters are misinformed? Then it's the opposite. And it's a total disaster. And you might wonder, what can we do in the situations where voters are misinformed? Well, you can read. I have a paper up there on my website on optimal, what are called representative democracy. So representative democracy is sort of what we have in the US, where you pick your representatives to vote for you, because by and large, as a population, we don't have time to get informed, even to the level of 55% correctness. Now. So do this exercise, it's useful. And this is really the fundamental idea behind aggregation, that you can get away and you can produce a very accurate classifier if you have many weak but still slightly better than average classifiers that are independent. And another reason I sort of encourage you to do this exercise is it's related to a theme that is deep and has run all through this course. And that is the E in to E out link. And that's the other place, or another big place in this class, where we saw independence. So independence has cropped up before. And it came to our rescue because that's what allowed us to establish the link between E in to E out. And we had to assume, in order to get that link, that your data was generated independently. And what's going on there is very similar to voting. If you have a lot of independent data points and each of them are giving you a vote, on whether your hypothesis is good or bad. Okay, and each individual data point is kind of a random data point. It's accurate with a low probability, but when you look at the average among many independent data points, they give you a very accurate picture of how you expect to perform out of sample. So similar thing is going on in the theory that we discussed. Okay, and similar thing can be made to work in the context of aggregation. Okay, just a nice little exercise. The world of Smurfs versus the world of Einstein. Do it and convince yourself of the power of aggregation of many weak but independent models. Okay, let's move to reinforcement learning. Okay.